Hi, welcome to the universe of first-order RC circuits. In this video, we will give you a practical and interesting example. The natural response of a first-order RC circuit where there is a conductor wire and a switch in series with a resistor and a capacitor. The switch, K, is initially open, ensuring that the capacitor current, IC, is zero and its voltage, UC, remains constant. The capacitor is charged with a voltage U0 at time 0. At that instant, the switch, K, is closed and remains closed from that moment on. We want to know what happens to the voltage and the current from that instant onwards, that is, for t equal or greater than 0. In here, you'll find math formulas, some illustrations, and graphs, so you can pause the video whenever you need a little bit more time to let the information sink in. But let's get to the point. The differential equation that describes the behavior of the circuit is as follows. In case you want to remember how to get here, you can watch our introduction video to first-order RC circuits. Well, according to the initial conditions that we mentioned, for t equal or greater than 0, the voltage U is 0. Thus, we can replace U by 0 in the differential equation. Then, to determine the voltage across the capacitor for t equal or greater than 0, we need to solve this first-order ordinary differential equation. First order because it has only the first derivative of one dependent variable, UC, with respect to an independent variable, t. In this equation, R and C are constants, and UC is the unknown. The solution to this equation is the following expression. The demonstration process of how to get to this solution is available in the first video on the Laplace transform regarding, of course, RC circuits. We can also determine the current through the capacitor, which is exactly the same across the source and the resistor for t equal or greater than 0, which is given by this equation. Well, but how do we get to it? It's easy, through the equations that we went through before. The current through the capacitor and the resistor can be determined by the famous Ohm's law that you probably know like the back of your hand. IR equals UR divided by R. In this circuit, the voltage across the resistor can be represented as UR equals U minus UC, in which U equals 0, so the voltage across the resistor equals minus UC. Ultimately, by replacing UC with the equation we saw above, we get our final expression, which is this one. Cutting things short, these are the equations that translate the natural response of a first-order RC circuit. But now, let's analyze the graphic representations of these expressions. After a time equaling R times C, the voltage across the capacitor terminals, initially charged with a voltage of U0, reaches 36.8% of that value. This time period, R times C, is called time constant, which is represented by the letter tau. After 3 times that time, that is, after 3 times tau, the voltage across the capacitor reaches 4.9% of U0. And after 5 times tau, it reaches 0.7% of U0. On the other hand, the IC current through the capacitor behaves in the following way. For the instant t equals tau, the IC current reaches minus 36.8% of its initial value minus U0 divided by R. At the instant t equals 3 times tau, IC reaches minus 4.9% of its initial value, and at the instant t equals 5 times tau, IC reaches minus 0.7% of its initial value. In conclusion, we can see that the initial value of UC of 0 equals U0, and the initial value of IC of 0 equals minus U0 divided by R. We can also see that as t tends to infinity, the voltage across the capacitor UC approaches its steady state, which is 0. And also that as t tends to infinity, the current through the capacitor IC approaches its steady state, which is equally 0. This shows that UC and IC only have transient states. But let's take a look at another situation. If the switch K is closed at an instant t equal to T0 instead of a time 0, we use the same line of thought, with only a few twitches. The voltage on the capacitor will be defined by this expression, and the current through the capacitor by this one. Therefore, the graphs obtained will be the following, where it is shown that the capacitor begins to discharge only from the moment T0 instead of at time 0. In the next video, we'll show you the forced response of a first-order RC circuit, so stay tuned! See ya!